Okay, hope this is working. All right, Unit 4, as I was saying before the video stopped, is a part of a 3-unit series. We're going to go from equilibrium to acid-base equilibrium to equilibrium of solutions. So when you've heard nightmare stories about AP chemistry, it was that solution equilibrium problem and unit that is the most challenging, probably of all the units. So why I'm telling you now is it's super critical that whatever we cover today, you really pay attention to. And throughout the unit, if you have questions, you've got to get your questions cleared up, or the next 2 units are just going to blow up. All right, so foundation is super, super important. So when we're talking about equilibrium, we are actually talking about a reversible reaction. Not all reactions are reversible, but the ones that are, we know we're at this dynamic equilibrium when the rate of the forward is equal to the rate of the reverse. So we already know about rates, right? So here we have our rate law for the reactants, if that's the forward direction. If the reactant's going in the other direction, we would have this as our rate law. If the reaction was going the other direction, that would be the rate law. Since the equilibrium is defined as when this rate is equal to that rate, we can set those rate laws equal to each other. And you see how you end up getting products over reactants if you're defining it in terms of your reactants. When you want to isolate the K, you get products over reactants. I'm never going to talk about this again. I just want you to understand where the K expression comes from. So whenever we're finding our equilibrium K, don't worry about this. Just know that it is products over reactants. Okay? Our important thing about equilibrium, in addition to finding when you are finding the K, is these exponents. These exponents are actually the coefficients in the balanced equation. So in your K expressions, you're going to do products over reactants raised to the coefficient. Notice that in this reaction that's shown to you, they're all gases. Gases and aqueous are the only states of matter that go in equilibrium expressions. Pure solids and liquids don't, because they're so high in concentration, they have very little effect. They don't change enough to cause any issues. The pure solids and liquids actually don't have a concentration. And do solids and liquids affect pressure at all? No, they don't. So we can also calculate something called a Kp, but that has to be gaseous systems alone. Okay, we cannot calculate Kp for aqueous systems at all. When you see K by itself, it's going to mean Kc with concentration. It's not going to mean, they'll never ask you for a Kp and not put a little p next to it. If there's just a K by itself, assume it's the concentration of products over the concentration of reactants. All right? And now you're allowed to use those coefficients in the overall equation to find what we call your expression. So what's important is the magnitude of K. So if you remember, when we went back there and we did our little demo this morning with the water tanks, you told me that products were greater than reactants. So what was the magnitude of K? Greater than 1. So if K is greater than 1, the forward reaction is favored. If K is less than 1, what does that mean? The reverse reaction is favored. What about if K is equal to 1? You guys fell into the trap. Does K equal to 1 mean equilibrium? Doesn't K greater than 1? Isn't it equilibrium back there when K is greater than 1? Right? Isn't it equilibrium if we have a K less than 1? So K equals 1 isn't at any more equilibrium than K greater than less than 1. If you have a K, you're at equilibrium. So what literally does K equal to 1 mean? What would your levels back there look like? That's when concentration is the same. The only time you have a K is equal to 1 is when your concentration ratio or your pressure ratio of products and reactants are the same. Okay, so please don't think that K equal 1 is equilibrium and the other Ks aren't. All the Ks mean equilibrium. Okay? Okay. There's a lot of K's in this class. All right. This is just a statement I need to make because it's going to show up and you're going to see problems. They're going to do all this work and they're going to tell you a temperature and you're like, why do I care about the temperature? That's because equilibrium constants are temperature dependent. If we do a lab and we determine it, we find K, which we will on Monday. You're going to find K in a lab. You have to know that that K is only good at whatever temperature we did, the temperature of the room when we did the lab. All right? So if they give you a different temperature, they're going to need to give you a different K. Got it? Okay, so you have these little graphs. You don't have the words written next to them, but you don't really need to write them. But what we want to do is figure some things out. The first thing we want to do is looking at these three substances. We're dealing with an equilibrium reaction. That's starting out not necessarily at equilibrium, but is eventually getting to equilibrium. So what are my reactants and or products? What are the reactants of this reaction or reactant? A. Why A? Yeah, it's decreasing in concentration. That has to be a reactant. So B and C have to be what? Products. All right. So now, what time-ish does it look like we reach equilibrium? A 1,000, that's kind of far. What are we looking for first? What are we kind of looking for? We're looking when all the lines stop changing slope. Remember, this is concentration over time. As our slope is the rate, concentration over time. So we want basically a slope that's no longer changing to indicate that the rate is no longer changing. So I'm thinking around here-ish, right? So I'm looking, I mean, 1,000 is not wrong. It is at equilibrium at 1,000, but I think it was at equilibrium before 1,000 too. So I'm going to say somewhere between 800, 850, somewhere in there. And again, I'm not going to sit there and freak out. I think 1,000 was a little far off. I might not give you credit for 1,000, but I'm not going to like pick hairs if you're somewhere obviously between here and here. All right? So now we have to do a balanced equation, and this is what I love because it's utilizing specifically stuff you learned in the last unit by looking at rate of decrease and rate of increase. When I do these problems, I like to pick just like the first block of time from like 0 to 250. And looking at that first block of time, don't even worry about the values. I just count blocks on the graph. This decreases, boom, boom, about 2 blocks, about 0.2 molar if you look at the things, right? A does-ish. How much does B increase? At what rate? About 0.1. That's about half the amount, right? So what does that tell you about the coefficients in the balanced equation? It's half of A, right? So what would I put for my one reactant's coefficient so far? 2, and then B currently would be 1 based on that. Now what about C? What is it doing in that 0 to 250 time frame? About a block. So what's its coefficient? 1. Make sense? We're going to do a couple of these really quick. They're all going to have the same equation. I picked bad examples. But at the end of the day, I need you to be able to look at these and kind of figure it out. So the next one, what are my reactants or reactant? A, my products. B and C. What time is equilibrium reached-ish? Yeah, 500 or 600, somewhere in there. 500 to 600 seconds. Please use your units. I didn't do units on the last one, so shame on me. Somewhere in there. And then the balanced equation. In that first block, let's see, from 0 to 400 minutes, 1, 2, 3, 4, 5, 6, 7, 8, close to 9 blocks. A is dropping. C is increasing 1, 2, 3, 4 and a half-ish. And B is increasing 1, 2, 3, 4 and a little bit. So it's kind of the same, right? A is doubled to B and C. So what's my balanced equation? B plus C. Be sure to use double-headed arrows when you're given these problems. I'm telling you now, these are on quizzes and tests, because I just wrote the test. Know how to do them. All right, next up, one last one. What time do we get to equilibrium? Yeah, I'm going with 800 seconds. And what would my balanced equation be? I'll let y'all count. Who wants to give me the equation? 2A in equilibrium with C, because A drops twice as fast as C does. Okay? All right. So one of the first problems we're going to work here is actually calculating the equilibrium constant, given all of these equilibrium concentrations. In order for us to calculate an equilibrium constant, we have to have the concentrations at equilibrium, not initial concentrations, equilibrium concentrations. So that makes this a simple problem. Now, here's a reality check that's going to happen whether you like it or not, in that anytime you have to solve for an equilibrium constant, Kp, Kc, I need to see an unsubstituted expression. Already know the rubrics of all the test questions. Points go to that. You cannot get a perfect score on a question if you don't write your unsubstituted K expression. Okay? So what is a K expression? It's just, we're going to find Kc because they give us concentration. It's just writing the concentration of your specific reactants, products over reactants, raised to the coefficients in the balanced equation. So these are all gases, so they all go into our expression. This is required for you to get any credit. Why am I doing that? Because that's how you get points on the AP exam. All right? That's going to be equal to, what am I going to put my HI? I'm going to put 0.3. Now it's just a plug and chug and solve. And writing this is helpful. It's going to keep you from making silly mistakes. Translating what you're writing and raising the coefficient at the same time without that expression. It's not impossible, but it's definitely a spot that you can make some mistakes. So what is to 2 sig figs my answer? I thought I heard someone say it. Someone say 50? Yeah. How do I make 52 sig figs? 50.5 with 50 with a bar. You can do this. You can do this. You can do this, which will just be annoying. Wait. You can do that. Good news. I do have good news. You do not need units on equilibrium constants. Okay? That's an AP thing, so I'm not going to make you do it. Just know that in kinetics, that kinetics K, it'll always say include units. But these equilibrium Ks, you're free to just write the answer with no units, and that's all you do. All right, so now we're going to have fun with K. We're going to play with K and do all sorts of things with K. And the first thing we're going to do is convert Kp to Kc and vice versa. All of this is a derivation. If you're interested, you can try to follow it. Don't really care, but what I do care about is you know the equation. Unfortunately, this equation is not on that AP sheet that you have, but I do want you to know it. So you need to memorize it. Trick to memorizing it. Because I always get confused whether it's Kc is equal to that. So best way to learn it, it is politically correct. You see it? Politically correct to the delta n. So I call this the politically correct equation. Politically correct. Now, what is all this stuff? Kp and Kc are obvious. R is the universal gas constant that we used in Chem 1 in gas laws. It's not the 8.314. That's the energy R. 8.314 has units of joules per mole K. Joules, does that seem important at all in there? No. What we care about has to do with this delta N, which has to do with gases. Remember, if we're going to have a KP, it's going to be a gaseous system. So we're going to use the gas R, which is 0.08206 latam molk. I call it latamolk. That is on the sheet. The only challenge you have is picking the right R, because they're both on the AP sheet right next to each other. So you need to make sure you know we use gas R, because I'm dealing with gases. All right? 8.314, the units won't work at all, so we don't want to use that one. And remember, you do need to memorize this. Now, what is that delta N? Delta N, delta means what? Change. The N is moles of gases. So delta N is the change in moles of gases. So if we look at this equation, for instance, how many moles of gases are on the left? 2. Here, 3. So my change is always based on final minus initial. Change in N in this case would be final minus initial. So our delta N would be 1. All right? Delta N is the change in moles of gases only. If I had any solids or liquids in there, I wouldn't count it toward my mole total. I'm only counting my gases. Okay? So here's the important part. Do I think they're going to give you a problem on the AP where you have to actually have to mathematically calculate KP or KC from this equation? No, I don't. However, I do think they may give you an equation where you have the same moles of gas on both sides of the equation. If I have the same moles of gas on both sides of the equation, what is true? KP is equal to KC. And I can see them doing that. And so to answer it, you would just say, hey, there's no change in moles of gases, so KP is equal to KC. And you wouldn't have to do any math. Why does that work? Some of you are looking at me crazy. Delta N of 0, if I have 1 mole on each side, for instance, delta N is 0. Anything to the 0 power is 1, so KP then will be equal to KC. All right, so before you ever do any math with this, find your delta N. If the delta N is 0, you're done. It's like a half-a-second problem. Okay? So let's do an actual problem with it. It's going to be a math one. We're not going to do the delta N. But I would first check your delta N. So what is the delta N, if that's a gas, for this problem? 2 minus 3, because I've got 2 moles here, 3 moles there, negative 1. All right, so I'm going to calculate. Ooh, my knee just almost gave out. I'm going to find K. Since they didn't list anything, we assume it's KC. And they gave us KP, so politically correct to the delta N. So KP is 0.25. I'm solving for KC. R is my universal gas constant. What is my temperature in the problem? 1100 Kelvin, another K, raised to the negative 1. So my Kc then to, let's do 2 sig figs, is equal to what? Calculators, get them out. We're going to have some more calculations going on this unit. Can I get a second on that? All right, 23. All right, questions on politically correct, converting KP to KC. All right, now we get to have more fun with K and talk about the different ways we can manipulate K by using Ks from other reactions. So right here, the very first thing you see is we already did this problem. Right? We solved 50 as the K for this. Notice the question then is what happens, or what is the K of this reaction? How does this reaction compare to that reaction? It's reversed, right? If it's reversed, products became reactants, reactants became products, what do we do to our K then if we want to find the K of this guy? Inverse, exactly. So that's what happens. If you reverse your reaction, you take the reciprocal of the K to find the new K. Got it? All right, now let's talk about what happens if we, what happens if we multiply through by something. So back up, this goes back up to the original equation. I should go down to here. What did I do to that equation on top to get this equation right here? What did I multiply through by? 1/2. When you multiply through, you're changing every single coefficient, right? What are the coefficients? Where did they fall in the equilibrium expression? They were exponents. So all you do is you raise the K to that number, whatever number you multiplied by. So we're going to take the original K of 50 and raise it to the 1/2, which is square root. So if I multiply this equation by 4, I'm going to raise it to the 4th. I multiply by 1/2, I raise it to the 1/2. Okay? And when you do that, you get the square root of 50 is 7.07. Okay? All right, and the last thing we can do to play with our K's is to add up equations to find a new K. So I'm just going to kind of go through to show you where it all comes from. If I have A going to B, do you agree that that's the K expression, B over A, right? If I have C going to D, do you agree that it's D over C? When I add these two equations up, I get A plus B gives me A plus C, sorry, gives me D plus B, right? So let's write the expression from here. It would be BD over CA, correct? So what do I do to combine this and this to get this? I multiply them. So, long story short, when you add equations, you multiply their K's. This is different than thermo. You guys have done something similar to this when you did the flippy thing in Hess's law where you added delta H's. I don't know if you remember that. You made it negative if you reversed the equation, and then you added them up, and then you just added the delta H's. When you're dealing with K's, when you reverse the equation, you take the inverse, and when you add up equations, you multiply. You multiply the K's. So let's put this to practice then. How would you see these kinds of problems? In something like this, equilibrium constants for the following reactions have been determined at 550 degrees Celsius. Calculate K, notice, at the same temperature. All they're saying is K, temperature is constant, so we don't have to worry about it, for the commercially important water-gas shift reactions. So this is what I term the goal equation. We're looking for the K of this equation, and we can manipulate those two equations in any way, shape, or form. When you're given multiple equations to pick from, it's probably a matter of you adding those two equations up. But we need to make sure they're in the right direction, or if they have the right coefficients and all that stuff before we actually do the adding. So looking at this first equation, what is it the sole source of that the goal equation has, but the other reaction up here doesn't contribute? Water and H2. Okay, do you see how the other equation doesn't have water and H2 in it? But what's bad about this equation? Where do we need our water and where do we need our H2? Yeah, we need to reverse that equation. So I always start with that first equation and do that. Yeah. Oh, I thought your hand was up. All right, so we're going to reverse this and we're going to write cobalt plus water gives us cobalt 2 oxide plus hydrogen gas. If I reversed it, that K1 is not K1 anymore. What did I do to it? What do I do to this K? I reverse the equation. Take the reciprocal. So that becomes 1 over 67. All right. Next equation. I think it's good because it's got CO, 1 CO, 1 CO2 where they're supposed to be. I'm just going to rewrite it the way it is. So that means I can leave the K as it is. So before we can assume adding them up gets us the right answer, let's go ahead and cancel things. I can cancel cobalt 2 oxide. I can cancel cobalt. Does what I have left over match my goal? Yes, it does. Since adding them led to the goal, what do I do with these Ks? Multiply the Ks. So K3 to 2 sig figs is equal to 7.3. Do we get it? This is the typical thing you may see. You also may see, which is not demonstrated in this example, you might have coefficients in your goal equation. Like if you had a 2 here, for instance, don't write that down. If you have a 2 there, you would have to multiply that equation through by 2. And if I do multiply it through by 2, what do I do to the K? Raise it to the 2. All right, so just be aware that that's something that can happen. So speaking of doing that, let's do our last problem, and then you guys can start on homework. Calculate Kc for the reaction. If Kc for this reaction is 1.3 times 10 to the 4th. So we're looking for this K. What did I do to this reaction, which I know the K of, to get to that reaction? Multiplied by 2. So what do I do to the K? Square it. So I know this is going to be something to the 8th. What is it going to be? 1.7 times 10 to the 8th is equal to our Kc for the new reaction. All right, so I think that's it. Is the next thing rice tables? Okay, yeah, we're done. So your homework. A lot of people keep coming and asking me questions about those particulate diagrams, and the reason they're struggling is because they're in black and white. Go to the homework online and open it up, and they're in color, and you should not have trouble, okay? All right, get cracking on that homework.